In this portion of the video cast, we'll take a look at the effect of temperature, pressure, change in volume, and change in concentration and addition of a catalyst, and how those affect the position of equilibrium in a chemical reaction. The guiding principle in this is using something called LeChats principle. And LeChats principle says that if a change is made to the conditions of a chemical equilibrium, then the position of the equilibrium will readjust so as to minimize the change made. LeChats principle can be effective, or can be used to guesstimate or to qualitatively predict. That means no numbers. Qualitatively predict how changes in concentration, changes in pressure, and therefore volume, because remember pressure and volume are inversely related to one another, and changes in temperature can affect how a chemical reaction will shift either to the left or to the right, to reactants or to products, depending on the change in that concentration, pressure, or temperature. Here's a list of how the changes occur. In terms of concentration, if you increase the concentration of a reactant or a product, it will shift to the opposite side. If you decrease the concentration of a reactant or a product, in other words, if you remove some, or if you remove a reactant or a product, it will shift to that side. Well, what do we mean by shifting? Well, here's an example. Let's say we have a pretend reaction of A goes to 2B. And both of these are gases, let's just say. And let's say, for instance, that we increase the concentration of A. We add some A to the system. Well, when we do that, we'll shift the reaction to the right, and therefore there will be more B. And so K would be increased, because remember, K will be equal to our concentration of B to the second power divided by our concentration of A. And we shift it to the right, therefore K will increase because we've increased the concentration of A. The removal of a substance can be illustrated the same way. Let's say that we remove some A. We just take some out. And the equilibrium will shift to the left to replace the amount of A that's gone. And since we removed an amount of A, then the equilibrium will shift to the left, then A's amount will increase. That's concentration. How about pressure? Well, when you increase the pressure of an entire system, not just one substance, but of an entire system, it will shift to the side with the least moles of gas. So if you increase the pressure, it will shift to the side of the reaction with least moles of gas. Shift to the side with the least moles of gas. If you decrease the pressure, then it will shift to the side with the most moles of gas. So going back to our hypothetical reaction, I'll rewrite it down here so it's a little bit larger. A goes to 2B, both gases. And let's say that this occurs inside a sealed vessel or sealed container, and we take the container and we increase the pressure. Okay, increase the pressure. Well, if we increase the pressure, it should shift to the side with the least moles of gas. Should shift to the left. And notice there's only 1 mole of gas on this side. If we decrease the pressure, like for instance expanding the volume of the container, then it should shift to the right, and it should shift to the side with the most moles of gas. Now, if there's more than 1 or 2 reactants or products, like let's say for instance there's 3C plus 1D. Now all of a sudden we have on this side of the reaction 2, 5, 6 moles of gas on this side and only 1 mole of gas on this side. So add up the total number of moles of gas just by looking at the coefficients of each one of them, as long as they're all gases. Remember, of course, this one is a solid, don't add it in there, and then there'd only be 5 moles of gas. Now remember, volume and pressure are inversely related. So the question could also be asked is, what happens if you change the volume of a system? So let's say, for instance, we had a container. I'll just draw it as a cylinder right here. And we take this cylinder, and we've got A inside of there, and some B and C and D, just like we've got in this reaction. And we take and we decrease the volume of the container. So the volume went down. Volume went down. Well, if you remember, volume and pressure are inversely proportional to one another as long as temperature and number of moles of gas are held constant. And remember the vice president, if one goes down, the other one goes up. Okay, anyway, we're decreasing the pressure. I'm sorry, decreasing the volume. So if the volume goes down, that means the pressure has got to go up. So if we increase the pressure, remember it says it's going to shift to the side with the least moles of gas. Therefore, the reaction would shift to the left if we were looking at this one right here and we actually had 5 moles of gas on one side and 1 mole of gas on the other. So be aware of that volume and pressure are the same type of change. It's just that they're inversely related. Let's look at the last change, temperature change, and how that can affect the conditions of equilibrium. Temperature is the one thing that if you change, you will change K sub C or K sub P. Okay? There will be a change in the equilibrium constant with a change in temperature. Just like there's a change in the rate constants or the change in the rate of a reaction if you change the temperature, there's also a change in the equilibrium constant if you change the temperature. Anyway, if you increase the temperature, of a reaction system, it will shift in the endothermic direction. And if you decrease the temperature, then it will shift in the exothermic direction. Okay, well, what do we mean by that? Well, let's just use a hypothetical example again. Let's say that the reaction is A goes to 2B. But let's add some additional thermodynamic data to this. And let's say that the delta H for this, in other words, the enthalpy for this reaction is negative 100 kilojoules per mole. Okay? And let's say that what we're doing here, having this exothermic reaction, is we're going to change the temperature. Well, what I invite you to do, or encourage you to do, is before you even look at whether the temperature is increasing or decreasing, is take a look at what the enthalpy data is telling you. And in this case, it's a negative 100, which means it is an exothermic reaction, right? If it's an exothermic reaction, that means that energy is being given off. So write energy, or heat in this case, as a reactant or a product. Since it's energy being given off, rewrite the reaction as A goes to 2B plus heat, because heat's being given off. And then when they tell you there's a change in temperature, look at it in terms of heat being a reactant or a product. And just like we did with concentration up here, say that it's increasing or decreasing in concentration. And those are easy, because if you increase the concentration of something, it'll shift to the opposite side. So let's say, for instance, in this reaction right here, since we're treating heat as a product now because it's exothermic, let's say that we increase the temperature of this reaction. Well, if we increase the temperature of this reaction, we're adding heat. We're adding heat right here, okay? Well, if we're adding heat to this side, which way is the reaction going to shift? The reaction should shift to the left, and therefore the amount of reactants should increase. Let's take a look at a second example. Let's just say, for instance, that we've got 2A plus B goes to 4C. And let's say that the delta H for this reaction is equal to 50 kilojoules. Notice it's an endothermic reaction in this case because delta H is positive. Well, let's say that the question asks, what happens if I increase the temperature of this reaction? I increase the temperature. Well, first of all, before dealing with the increase in temperature, take the delta H right here and make it be a reactant or a product. Well, since it's a positive delta H, make it be a reactant. 2A plus B plus heat goes to 4C. Well, if I increase the temperature, I'm increasing the amount of heat right here. And just like if I increase the concentration of A or B, I'm going to shift the reaction to the opposite side. So therefore, the reaction should shift to the right. It should shift to the right because I'm increasing the amount of this by saying I'm increasing my temperature of my reaction. How about if I decrease the temperature of this? If I decrease the temperature of this, then I'd actually, in effect, be removing some of this heat. Well, if I remove a concentration of a reactant or a product, it's going to shift to that side. And therefore, the reaction would shift to the left the reaction would shift to the left to replace that heat that's been removed. The last thing that can affect, or at least be thought to affect, the status of equilibrium is the addition of a catalyst. And this is a little bit of a misnomer, actually, because a catalyst does not affect the situation of equilibrium at all. A catalyst, remember, only speeds up the reaction. And so it speeds up the reaction reaching to equilibrium. It gets you to equilibrium faster, but it does not change the status of the equilibrium. There's no change in K, whether it be C or P or whatever the K is. There's no change in it at all. All it does is speeds up the reaction and gets you to equilibrium quicker. Okay, now let's take a look at some example problems applying Le Chatelier's principle. Let's take a look at this example problem right here. 2A gaseous plus B gaseous goes to 3C plus D. And notice the delta H is a negative 100 kilojoules. What type of reaction is this? Since it's got a negative sign right there, it means it's an exothermic reaction, which means technically what you could do to this side of the reaction is write plus heat and just say that there's a certain amount of heat being given off as a product in this reaction. Okay, what happens if we increase the temperature of this system? Well, if we increase the temperature, that means we're increasing the amount of heat, correct? If we increase the amount of heat, that means this concentration right here will be going up, and so we should be driving the reaction to the left. Driving the reaction to the left. So we can say that it shifts to the reactants. It shifts to the reactants because we've added some heat to the system. Okay? Second question. What happens if I increase the pressure of the entire system? Increase the pressure of the entire system. Well, remember, if you increase the pressure, it's going to want to shift to reduce that stress. So it's going to want to shift to the side with the least moles of gas. Well, add up the moles of gas here. 2 plus 1. There's 3 moles on this side. If you look on this side, there's 3 plus 1. There's 4 moles of gas on this side. And so we say that the reaction should shift to the left to reduce that stress, or to the reactants side. Shift to the reactant side, or to the side where there's A and B. Another way to ask this is what happens to the concentration of B, or what happens to the amount of B. And you could say B would increase because you would have increased the pressure of the system and driven it to the side of the least moles of gas. Okay, lastly, let's look at this question. What happens if I increase the concentration of A? So I've added some A now, increase the concentration. Well, remember, if you increase the concentration, just like if you increase the amount of heat, you're going to shift the reaction to the right, or you're going to shift the reaction away from that one. So we'd say that the reaction would shift right, and therefore we'd have an increase in C, and therefore an increase in D. We'd have more of the products in that case. How about volume, though? How does volume affect the system? Let's take a look. Let's say we decrease the volume of the system. Well, let's say that this reaction right here takes place in a closed container. Closed container, let's say it's a cylinder, and we take a piston and we push down on it. We decrease the volume, okay? We shove it closer. What happened to the pressure inside of the system? Well, if I decrease the volume, remember, I've increased the pressure, right? Hey, now it becomes a question just like this one. If I increase the pressure, remember, I'm going to shift to the side with the least moles of gas. And so if I decrease the volume right here, I'm actually increasing the pressure, and therefore it should shift to the side with least moles of gas, which is, in this particular case, 3 moles of gas on the left. So it should shift to the left. How about if I increase the volume? Well, it'll be the opposite. Then I'll actually be decreasing the pressure, right? If I decrease the pressure, then it'll shift to the side with the most moles of gas, what happens to be to the right. So C and D should increase. How about if I add a catalyst to the system? Okay, if I increase the reaction rate by adding a catalyst, then the reaction will speed up. Okay, the reaction speeds up, and I reach equilibrium sooner. Okay, remember from chapter 14, when you add a catalyst to a system, you actually change that amount of the pathway of the reaction, and usually the activation energy is lower, and that's what speeds it up. But does it affect K? How does it affect the equilibrium constant itself? Remember, there's no effect at all. no effect at all on K. Okay, we'll reach equilibrium sooner, but we won't affect the actual equilibrium itself. Okay, now let's take a look at this handout that you should have. This handout talks about the effective conditions on the position of equilibrium and reinforces some of the things we've been talking about with Le Chatelier's principle. So find this handout, the effective conditions on the position of equilibrium, and pause the video if you need to, just to make sure that you've got this in front of you. Let's take a look at this table. This is table 8.1, and it says the effect of changes in conditions on the position of an equilibrium. And this summarizes pretty much everything that we've talked about earlier in the video as well. It says if I increase the concentration of a system, it'll shift to the opposite side. Is there a change in K? No. If I decrease the concentration, it'll shift to that side. Is there a change in K? No. Increase and decrease in pressure. And remember, pressure and volume are inversely related, and so they could ask you a question, what happens if the volume is decreased? Well, that means the pressure is increased. Therefore, it shifts to the side with the least moles of gas, and there's no change in K sub C. Notice these two, the increase and decrease in temperature. They're the only two right here where you have a change in K, where you have a change in the equilibrium constant itself. Increase in temperature shift to the endothermic, and decrease in temperature shifts to the exothermic direction. Remember, with these two, it's easiest to treat heat as a reactant or a product, and then just think of it in terms of increasing or decreasing the concentration of that heat. And then lastly, adding a catalyst. Remember, there's no change in or no effect on the equilibrium, but there is a change in K, and there's also no change in K sub C. Catalyst just speeds up the reaction. Let's turn in this to some of the sample exercises. Your page might actually have these questions a little bit smaller, and so you can see them a little bit, a few more of them at one time. But that's okay. This one's just a little bit bigger, and you might be able to see it on the screen a little bit better. Let's start with question number 2 right here. Question number 2 states, which one of the following will increase the rate at which a state of equilibrium is attained without affecting the position of equilibrium? Will increasing the temperature, remember, temperature will increase the reaction rate, but it will also affect the position of the equilibrium, because remember, it will change K. How about increasing the pressure? Well, remember, if you increase the pressure, you're going to shift to the side of the reaction with the least moles of gas, and so you will be affecting the position of the equilibrium, correct? You'll be shifting it to the least moles of gas. Decreasing the concentration of the products, it's just like removing an amount of substance from the system, and therefore it will shift to that side and it will affect the position of the equilibrium. And lastly, adding a catalyst. Well, of course, that will increase the rate of the reaction, but it will not affect the position of the equilibrium. So the best answer for number 2 is D, as in dog. Let's take a look at question number 3. In the manufacture of methanol, hydrogen is reacted with carbon monoxide over a catalyst of zinc and chromium oxides. And the following equilibrium is established. And you can see here there's 2H plus CO yields CH3OH. And notice this is an exothermic reaction. So technically, stop right there before you even read any more of the question and put plus heat, because we know that heat is given off, and heat is technically a product in this case. Which one of the following changes would increase the percentage of carbon monoxide converted to methanol at equilibrium? So in other words, what we want to do is we want to take more of this carbon monoxide and convert it to methanol. More of the carbon monoxide and convert it to methanol. Take a second and look at the examples, at the questions. Pause the video, and then we'll come back and answer the question. Okay, let's come back and talk about the possible answers. Letter A says decreasing the total pressure. Well, if we decrease the pressure, remember it's going to shift to the side with the most moles of gas. Most moles of gas. If you look over here, there's 3 moles of gas on this side. And if you look on this side, there's 1 mole of gas. Well, the reaction would shift to the left, and in effect, we'd be increasing the amount of CO. Remember, the question wanted to take the carbon monoxide and convert it to methanol. Well, we're not actually doing that, so A is not a very good choice. Letter B, increasing the temperature. Well, if we increase the temperature, we're in effect adding heat to the reaction. Well, if we add heat to the reaction, that means we're adding like more of this substance right here. If we increase the concentration of that, that means it's going to shift to the opposite side to reduce that stress, and so it will shift to the left. So that's not a very good choice either, because we're not getting rid of the carbon monoxide and changing it to methanol. Letter C says increasing the proportion of hydrogen gas in the mixtures. Well, now we're increasing the concentration of this. We're adding more of this stuff. If we add more of this, it should shift the reaction to the right, because it wants to reduce or relieve that stress. And so we should be taking more of this carbon monoxide at the same time and shoving it to the right and making more methanol. So C is a pretty good choice. C is the best choice, actually. And it allows it to shift from left to right. And then lastly, increasing the surface area of the catalyst. Well, that should speed up the reaction rate, right? But it doesn't have an effect on the equilibrium. Let's look at the next page and another one of these questions. This is question number 4, and yours might be on the same page already. I'm not sure, but it's probably a little bit smaller than this one. But let's read through the question, then we'll pause and give you a second to try to answer it. When heated in a sealed vessel, ammonium chloride is in equilibrium with ammonia and hydrogen chloride according to the equilibrium. Increasing the temperature increases the proportion of the ammonium chloride that is dissociated. So if I increase the temperature, more of this disappears. In other words, it shifts to the right. The best explanation for this is that, go ahead and take a moment right now and read through A, B, C, and D, pause the video, and we'll come back and answer the question. Okay, hopefully you've had a second to pause the video and take a look at the answers. Let's look at them backwards. Let's look at letter D first. This decreases the rate of both reactions, but the reverse of the rate is affected more than the forward reaction. Notice it says it decreases the rate. Well, it says right here that we increase the temperature. And remember, if you increase the temperature, you speed up the molecules, and therefore you speed up the reaction rate. So D is not a very good choice, because we're technically increasing the reaction rate, not decreasing it. Letter C, this increases the rate of the forward reaction, but decreases the rate of the reverse reaction. Well, I would agree that it does increase the rate of the forward reaction, because you increase the temperature. Molecules smash together more, and it should shove it, or should increase the rate of the reaction. And we're told that it decreases the amount of NH4Cl that's dissociated, so the forward reaction is going faster. But it says that it decreases the rate of the reverse reaction. Well, how can you increase the temperature and not have more collisions and therefore a faster reaction? So C is not a very good choice either. Then letter B, this increases the rate of both reactions, but the reverse reaction is affected more than the forward reaction. Well, I'd agree that it increases the rate of both reactions because you increase the temperature, right? But if it affected the reverse more than the forward, that means the reaction would actually be shifting this way, and we'd be creating more of the NH4Cl. And it tells us in the question that we're increasing the proportion of ammonium chloride that is dissociated. Okay? We're breaking more of this up, not making more of it. So B is not the best choice. And then letter A, this increases the rate of both reactions. We agree that that's true. But the forward reaction is affected more than the reverse of the reaction. Best choice right there, because the forward reaction is the one that's going to make the dissociation of NH4 more possible. Let's go on to the next question. Number 5 says, when methane and steam are passed over a heated catalyst, the equilibrium below is established. Which one of the following will result in a change in the value of the equilibrium constant, K sub C? Pause the video and see if you can answer the question. We'll come back in a moment. Okay, hopefully you've had a moment to read the answers and come up with your own answer. First of all, letter A, increasing the pressure. Well, increasing the pressure will shift the reaction to the side with the least moles of gas, but will not change K sub C. Adding methane, that'll shift it to the right, but it won't change K sub C. And letter C, decreasing the concentration of water, well, that'll shift it to the left of the reaction, but it won't change K sub C. Remember, the only thing that will change K sub C is by changing the temperature. And so D is the best choice. If you forgot that, take a look back at this table that we just introduced to you a second ago. Which are the only things right here that will change K sub C? We're not saying that it won't shift the equilibrium, but we're saying that it will actually change the equilibrium constant itself, the ratio of products to reactants. And an increase in temperature or a decrease in temperature are the only ones that will change that. Let's go on to the next question. Number 6, when 0.1 molar aqueous solutions of silver nitrate and iron 2 nitrate are mixed, the following equilibrium is established. Here's the equation. Which of the following changes would produce more silver? So they're wondering which one's going to produce more of this solid silver over here. Pause the video, try to answer the question. Okay, hopefully you've had a second to find an answer. Letter A, adding some iron 3 nitrate solution. Well, iron 3 nitrate is this substance. Oops, a 3 right here. And remember, that'll dissociate, and it'll form Fe plus 3. And it'll also form some NO3 minus, 3 of them as a matter of fact. But we'll actually be increasing the Fe plus 3 concentration and increasing the amount of Fe plus 3 dissolved in the solution. Well, if you increase the concentration of this stuff right here, you should drive the equilibrium to the left. That's not what we want to do. We want to drive the equilibrium to the right and produce more silver. So A is not the best choice. Letter B, adding more iron 2 nitrate solution. Well, now you're adding some iron FeNO3 2, which when it dissociates, it gives you some Fe plus 2. Hey, what's this stuff right here, Fe plus 2? If I increase the concentration of this, which way should the equilibrium shift? Well, it should shift to the right, correct? And it should give me more Fe plus 3 and more silver. Hey, that's the thing I'm looking for, so B is definitely a good possibility. Removing some Ag plus ions by forming an insoluble silver chloride. So let's say I add some chloride, some hydrochloric acid to this. Now I'm going to take and precipitate some of this Ag+. Well, if I do that, I'm actually decreasing the concentration of Ag+, and the reaction should shift to the left. That's not what I want to happen. I want this to increase. And lastly, increasing the total pressure. Well, if you look, all of these substances are aqueous or solid. Well, pressure shouldn't have any effect on it because remember, pressure, if you increase, should shift to the side of the least moles of gas. We don't even have any moles of gas in this one, so it's not going to make a big difference. So 6th best answer is B. Let's take a look at number 7. In the conversion of nitrogen to ammonia using the Haber process, the main reason why the temperature is limited to about 400 Celsius is because you can go back and read this packet and find that answer. Let's skip on that one. Let's turn to number 10 back here on the opposite side. Nitrogen monoxide and oxygen react together in a reversible reaction to form nitrogen dioxide. Describe, in terms of rates of reactions and the concentration of the species present, the way in which equilibrium is established if nitrogen monoxide and oxygen are suddenly mixed in an empty flask. Well, we've got nitrogen monoxide and oxygen coming together in a reversible reaction to form nitrogen dioxide. Well, in terms of the reaction rates, or rates of the reaction, if we graphed this, we'd say that we'd have a certain amount of nitrogen monoxide. Okay, this is NO, and this would be time. And we'd have a certain amount of oxygen when we started, and this would be time as well. And as time went along, we'd say that NO would decrease, and we'd say that O2 would decrease, and we'd say eventually they'd reach a certain amount, and they'd stay constant. Okay? At that time, we would have reached equilibrium, and we would have created some NO2. Second, write a balanced equation for this equilibrium, and I've almost got a balanced equation right here, but I happen to have 3 oxygens on this side and 2 on this side. So to better write this reaction, let's put a 2 right here in front of the NO, which means I need to put a 2 right here in front of the NO2, and now I have a balanced equation. And I should put G down here because all these are gaseous products and gaseous reactants. And then letter C, nitrogen dioxide is brown, whereas nitrogen monoxide is colorless. So this side has no color, and this side over here, it is brown. Okay? This side of the reaction is brown, this side's no color. All right, if the oxygen is replaced with an equal volume of air, the mixture of gases becomes lighter colored. Explain why this occurs. Well, we replaced it with air. What's air made out of? Well, air is what, about 78% oxygen? No, 78% nitrogen and about 20% oxygen, right? So in effect, what have we done to this? If we've taken the oxygen away and replaced it with something that's the same volume, but now it's only 20% oxygen. Well, we've decreased the amount of oxygen in the system, right? Since we removed some of the oxygen, Le Chatelier's principle says that it should shift to replace that or adjust to that stress. And so the reaction should shift to the left. It should shift to the left. Why does the gas become lighter colored? Well, because more of it became NO. And remember, NO has no color, and NO2 is brown.